section, very first thing I had written this expression for the DM interaction, which is not quite the right expression, but something wrote down today. So we should go back and correct it. I just wrote it down from memory, which as one grows old doesn't serve you as well as it should. So we've been talking about basically sort of cooperative phenomena in magnetic systems. In particular, we've been looking at ferromagnets, right? So the ferromagnets, the cooperative phenomenon is such that at high temperatures, the system is in a paramagnetic state, but there is no magnetization. I mean, I'm assuming always that the external magnetic field is equal to 0. Whenever you have an external field, you will always have a magnetization in the direction of the magnetic field. So something, nothing very interesting happens. But if you don't have a magnetic field, then at high temperatures, typically the system is in the disordered phase, and we have water parameter being the magnetization that equal to 0, whereas as you go below TC, one develops a spontaneous magnetization. So this is the phenomenon. This is the cooperative phenomenon that one is trying to understand. But before going into actual calculations and so on, what we would like to point out is that this is actually something which is highly unexpected. Why is it unexpected? So you have a magnetization. Let's say in the Ising model. The energy doesn't matter whether you can flip all the spins. You get back the same energy, right? Without the magnetic field, the Ising model has this symmetry, up-down symmetry. That if I change the sign of all the sigmas, since energy depends on sigma I, sigma j, when you change the sign of sigma I as well as the sign of sigma j, energy doesn't change. Right? So let's just write that down. We have a Hamiltonian, and now the simplicity of writing Ising model, the same thing will apply also for Hilbert model and something similar models. Here is sigma I. So it just says that's the form of that. This energy is invariant. Doesn't change. Sigma I going to minus sigma I for all I. Right? It's clear to everybody, right? I mean, it's sigma 1, sigma 2, sigma 2, sigma 3. If all of them change sign, then the energy doesn't change. Right? Now, what are you told in sort of when you do statistical mechanics, let's say canonical ensemble, Boltzmann probability, etc.? You are told that the probability that a particular spin configuration will operate in an ensemble is basically 1 over some partition function exponential minus this energy h sigma I divided by kb. This is the standard Boltzmann probability. Given a microscopic state, you look at the energy of that microscopic state, divided by kVt, put that in the exponent, that will tell you the probability that that particular state will occur in your ensemble. So when you calculate averages, you are supposed to take into account all microscopic states with the appropriate probability. Now what does it say? If you combine these two, so this says that if I now actually believe this statement, then P of sigma I is the same as P of minus sigma I. Right? You see the logic, no? I mean, these two states have the same energy. So I flip the signs of all the states, I get back the same energy. So according to canonical ensemble, these two states will occur with the same probability. But if that is true, then you cannot do magnetization. because I just take any state in your ensemble and flip the spins, and the new state that I get is the same probability as the old state. When I average, we'll always get sigma I average equal to 0. Right? Is that clear to everybody? I mean, this is something that actually is very, very fundamental to sort of understanding phase conditions and so on. So these two states, according to the symmetry of the Hamiltonian, these two states have the same energy. And according to the canonical ensemble, these two states should come with the same probability in your ensemble. But if these two states come with the same probability in your ensemble, then sigma I, if this is true, then that has to imply sigma I average. Right? So, I mean, if you want to have a spontaneous magnetization, a ferromagnetism, where sigma I average is non-zero, then something has to change in this description. Okay, you see the contradiction, right? Let us change the signs of all the spins. The state has the same energy, so we pass according to the standard Boltzmann picture. That should come with the same probability. So then I have average sigma I average over both these states. They come with the same probability. So the average must be equal to 0. So according to this argument, you can never have ferromagnetism. But in reality you do. I mean, you have magnets, which people know that even without a magnetic field, they exhibit non-zero magnetization. So what happens? So this is related to, the description is related to symmetry. So you have to look at the symmetry of the Hamiltonian. Hamiltonian has the symmetry. The Hamiltonian is invariant under sigma I going to minus sigma I for all I. But going from here to there is no longer that. The ensemble that system actually explores in low temperatures does not obey the symmetry of the Hamiltonian. That all symmetry related states, which by definition have the same energy, but they are not explored with the same probability in the low temperature phase. So I mean, when the system, in this case, the ordered state is twofold. I mean, one can have a state where ground state where everything is pointing up, basically meaning sigma equals +1. There is exactly the same energy state is there, where everything is down. These two states have exactly the same energy. But if you actually look at this behavior of this model, and let's say at 2 dimensions, you go below DC, then you will see either this sector or that sector. You don't see both of them at the same time. If you see both of them, then you average about both of them, then everything will be equal to 0. So this is no longer true. But T less than some critical temperature. And this phenomenon that we actually have the thermodynamic state breaking the symmetry of the Hamiltonian, that is called what?
Spontaneous symmetry.
Right. That is called spontaneous symmetry breaking. System is doing it by itself. And spontaneous basically means that your system is doing it by itself. You can add this a magnetic field term which will break the symmetry again. As soon as you put in magnetic field, then sigma I minus sigma no longer do that. Symmetry is broken. But that symmetry is broken by a term in the Hamiltonian. Here there is no such term. H is equal to 0. Hamiltonian still has the global flip up-down symmetry. But if you have that symmetry, then you cannot have spontaneous magnetization. So the state that the system explores, the set of states the system explores at low temperatures, low meaning T less than Tc, will be either in the upspin sector or in the downspin sector. you do an experiment, you cannot predict beforehand which sector it will go into. That will depend on the dynamics, the knowledge of the system experience, and so on and so forth. The system will go into one of the sectors, it will go T less than BC. And it will go to both these sectors with equal probability. That is where the symmetry of the Hamiltonian comes in. That there is no energetic difference between this sector and that sector. So if you do 1,000 experiments, on the average 500 of them will give you positive magnetization, 500 of them will give you negative magnetization. But a particular experiment will give you either positive or negative. Below this, you cannot say that I pull the system down to below this, I see now positive magnetization, after a little while I will see negative magnetization. That will not happen. And that is basically, system is doing this, making the spontaneous symmetry spontaneous. Question is now what goes wrong? In the sense that if this is true, then this is cannot be true. Because H sigma and H minus sigma, they have the same energy. So, but the thermodynamic state is breaking the symmetry, and the way that it is doing it is there are many mathematical ways of doing that. But physically, what is happening is that once the system gets into this upspin sector, then it cannot go into the downspin sector. Although that other states of equal energy sitting somewhere else, system cannot make a transition from positive magnetization to negative magnetization by itself. And the reason that it cannot do that, is something that we have already discussed to some extent. So, let's say that system has gone into this sector. You pull the temperature, T less than Tc, at some point you find that the magnetization is positive. Now my claim is that if the magnetization is positive, then going from here to there requires going over barriers that diverge in the thermodynamic. So that process is not going to take place when you go to the infinite system size image. By the way, mathematically one can show that this spontaneous breaking of symmetry is possible only in the thermodynamic. Any finite system will not actually exhibit spontaneous symmetry breaking. Some limiting procedure is to be done to get the system size go to infinity. So let's see why that happens. So I want to start from this, not everything up, but majority of them up, and then I want to go to this sector where the majority of them are down. How to do that? Do that, one has to be intermediate state, which looks something like this. One cannot just go in one step from all up to all down. It has to go through intermediate steps, and it has to do by basically flipping one spin at a time and so on and so forth. So if you want to go from positive to negative, then there has to be this domain volume. Intermediate state will have a domain volume, which part of the system is positive, part of the system is negative magnetization. And what did we say about the energy of such domain volume? Let's say in 2 dimensions.
Very large.
Proportional to the size of length of the system. In thermodynamic limit, the energy was 20. So, spontaneous creation of a domain volume, which is necessary in going from the upspin sector to the downspin sector, doesn't take place in the thermodynamic limit, because for that one has to go over a barrier that diverges in the thermodynamic limit. So this is basically why you have this. That once you get into this state with positive magnetization, although there is an equally probable state with negative magnetization with the same energy, but the system cannot explore both of them at the same time. And that, in some sense, this is a sort of algorithmic way of saying that why one has this kind of symmetry breaking. But there are more rigorous mathematical ways of doing that, but that requires a lot of mathematics, which I don't want to go into. But this is the phenomenon that every time you see some kind of a magnetic ordering, what is happening is that we are changing some parameter like temperature or magnetic field or whatever we are changing, high temperature is easier to deal with temperature. Magnetic field in this particular case actually gets rid of all phase transitions. Why is that? Because magnetic field, if I put in, there will be a non-zero magnetization at all temperatures. Because magnetic field says that single spin, its energy when it is aligned with the magnetic field is going to be lower than the energy when it is the other way around. So even if there is no interaction, it will always have magnetization. And as you are changing the temperature, it's just go from small magnetization to large magnetization. There is no particular temperature at which something critical happens. So this phase transition is there only when magnetic field is equal to 0. Magnetic field equal to 0 basically means that the Hamiltonian has this up-down symmetry, and that symmetry is spontaneously broken by the system as it goes from the high temperature phase to the low temperature phase. And one simple way of understanding what is happening is that if it goes into one of these sectors, then from there it wants to go to the other sector when the probabilities are the same. But intermediate states will have very high energies, and so this kind of transition between the going back and forth between this sector and that sector, that is not allowed. And as a result, when you do the average, we average only over the states in one of the sectors, and that gives you a non-zero value of it. And this is actually one of the things that, again, we're talking about P.W. Anderson. There is a famous article by P.W. Anderson, it is called Mode is Different. That when you have a large number of interacting objects, then you see some properties which you wouldn't expect just by looking at the microscopic Hamiltonian. So if I just look at the microscopic Hamiltonian, I would say that yeah, it's a symmetry. Cos sigma and minus sigma are the same. They have the same energy. So there would not be any possibility of any non-zero value of sigma either. And if you have just four spins or 5 spins, then you can simulate it on your computer. And you will see that it will keep on going back and forth between upstate and downstate. And if the average is long enough, it will be equal to 0. So you have to really go to a system size going to infinity limit. Infinity limit also is an abstraction. There is nothing. In the lab, there is nothing infinite. But the point is 10 to the 23. Typical number of spins that you have in your macroscopic sample is large enough to say that these kind of transitions from one sector to another that we'll never see in the lab. So this is one concept that you must appreciate whenever you are looking at magnetism, and in particular the cooperative phenomena, which lead to various kinds of transitions and so on. So most transitions, there will be also some kind of a spontaneous symmetry breaking, and it is very important to understand what symmetry is being broken at the transition, because that is necessary to define your order plan. There is another concept that is very crucial to understanding phase transitions, that you have to define for your particular system appropriate order parameter, which is by definition equal to 0 in the high temperature phase, and which takes a non-zero value as you go to T less than T0. And this order parameter, definition of that must, in some sense, take into account the particular symmetry that is being broken at the transition. Yes.
One question. So is this a classical or a quantum effect, this spontaneous symmetry break?
No, I think model is purely classical.
But say spins were quantum.
Yeah,
But
quantum model is also will exhibit spontaneous symmetry. If you look at the Heisenberg model.
Yeah. So one would then like we can also have a state which is a superposition between all up and all down, right? Why is that forbidden?
So I mean, you have to prepare the system in that state.
Yeah.
You can write down whatever linear combination of states that you want. But the question is, in reality, does the system actually can be in a state?
What What if I start with that state?
You can, I mean, in the lab you can try to start, but we'll find out that, it's impossible. In the sense that, again, when can you take a linear combination? You can do it by hand on a piece of paper. But somehow one has to, in the lab, one starts with, let's say, one of the states that there has to be a perturbation that will connect it to the other state that we are looking at. And that perturbation has to be sufficiently strong so that one can actually have a transition from this state to that state, or mixture of this state to that state. But this is, again, a good question in the sense that, there are quantum fluctuations. And quantum fluctuations can destabilize an ordered state. So here we are talking about basically thermal fluctuations. But let's say at very low temperature, zero temperature, close to zero temperature, then there are no thermal fluctuations. And then the question is whether certain ordered states are stable or unstable under quantum fluctuations. And quantum fluctuations can actually, in some sense, get rid of the ordered state. Some. Okay, so I was talking about the order parameter. So the order parameter has to be defined in such a way that it has to discriminate between ordered states which are related to each other by symmetry. So the order parameter has to be defined in such a way that these two states are related to each other by symmetry. These two are equally good ordered states. Order parameter must distinguish between what is happening here and what is happening here. And that, define a particular order parameter like that, requires some understanding of the symmetry that is being broken at the phase transition. So here it is simple. Here it is just a sigma average. So sigma average is plus something here and minus something there. That's easily distinguishable. But in some other cases, one has to be a little careful in defining appropriate order parameter and appropriate order parameter field, which is suitable for that particular symmetry breaking that we are trying to study as a phase transition. And maybe, I have one more lecture tomorrow. We may try to give you some examples of how to, just looking at the symmetry and from that how to construct the order parameter that is appropriate for that phase transition. This concept of symmetry is very important. Keep in mind, because again, there is this very interesting thing. Study of phase transitions very interesting because of many things. But one very interesting thing is what is known as universality. There are many different phase transitions which don't apparently have anything to do with each other. They have the same behavior near the phase transition. And there, the symmetry plays a very important role. Okay, so far we've been talking about ferromagnetism. So today at least I take some time to talk about some other kinds of magnetic order that are possible. Again, there's a huge number of different kinds of ordered states that you can have in magnetic systems. I will just talk about a few of them that are sort of more common, more. So apart from ferromagnet, the other sort of magnetically ordered state that everybody knows about is an antiferromagnet. So the antiferromagnet is very closely Hamiltonian, one can be written again something as I had done there, J nearest neighbor pairs, sigma I, sigma J. This is the Ising model. I mean, I can also look at Heisenberg model where instead of sigmas, I will have Si correlated to Sj and so on and so forth. Exactly the same form in Hamiltonian, but now we have J less than 0. J negative. Same Ising Hamiltonian, but we are putting in the coupling constant, which was positive in the case of ferromagnet. Positive in the case of ferromagnet, saying that when I have these two, both of them with the same sign, then you have the ferromagnet that is a lower energy. But now, if both of them are the same sign, if J is negative, then that corresponds to a positive. So that will have a higher energy. And the state with one up and one down, that state will have a lower energy. So that is how the system is going to order, if any. So, this one exercise that you can do. One exercise is that take this again on a line, one-dimensional case. Thermodynamics of that will be the same as that for a ferromagnet or different? You use the same procedure that I had told you about. That you have this partition function into the beta J, sum over nearest neighbors, sigma I, sigma J, and then you have to do a trace of this, sum over all possible values of the sigmas. So if you do that, there is no magnetic field. When you have magnetic field, then the situation becomes a little different. But no magnetic field. Will it give the same result for plus J and minus J? So what did we find? When you have a line with open ends, let's go back to your notes and find out what is the expression for the partition.
It will get the same. It's cos x, so it will be the same.
It will be the same. So this is basically, we calculated that 2 raised to the power n cosine hyperbolic beta J raised to the power some n minus 1 or something. This was what the partition function is. Now, if you change the sign of J, does this thing change? Cosine hyperbolic, it is an even function. So, thermal properties of this will be exactly the same as that of ferromagnet. And there is actually, I think, the problem set that I gave, there was one problem that maps the ferro to the antiferro or antiferro to the ferromagnet, simply by doing a transformation in a sublattice. Now, 1D lattice is trivially can be divided into 2 sublattices. Right? I mean, 1D lattice is like this. Etc. Now, I said that if the other side is in one sublattice, I call this. These are identical, I mean, as far as nothing is different between them. But this process I will call one sublattice and the zeros I will call second sublattice. And the kind of ordering that we are going to have is antiferromagnet. They want to be antiparallel. So we will have a of course, 1D there is no ordering, but this is the tendency for the space to be like that. So as you can see here, all the sides marked by zeros, they want to be down. All the sides marked by x, they want to be up. So this is the property of antiferromagnet, that if you can divide your lattice into 2 sublattices, such that if I now look at one sublattice and its neighbors, they belong to a different sublattice. That's how sublattices are defined. That is called a bipartite lattice. That if you have sublattices A and B, so if you look at S plane in sublattice A, then all its neighbors are in sublattice B and the other way around. If you look at S plane in B, then all its neighbors will be in sublattice A. So this height of an interaction says that one sublattice wants to be up, other sublattice wants to be down, or the other way around. I mean, I could have equally again. This Hamiltonian has this up-down symmetry. So I would have chosen the spins in this sublattice to be down and the other sublattice to be up. So in such a case, one can do a simple transformation. One can just call a new set of spins. So I'll call here tau I equals sigma I if I becomes to sublattice x, and I will call tau I equals minus sigma I if it's another sublattice. Then I write the Hamiltonian in terms of this taus, and that introduces a negative sign which converts antiferro to ferro. So there is a global transformation that one can do simply by changing the signs of the spins in one of the sublattices, and that maps the antiferro problem to the ferro problem as far as thermal properties are concerned. Whenever you have a magnetic field, you cannot do that anymore, because magnetic field then will couple to the taus in one sublattice in one way and the taus in the other sublattice in a different way. Because you have a magnetic field which is like minus some whatever h times sum over I sigma I. This is the magnetic field term that we have in the Hamiltonian, h and the sum over I sigma I. And here, if I make this transformation, sigma I write in terms of the taus, then the taus in one sublattice will come with plus h, the other sublattice will come with minus h. So then that's not, symmetry is broken. You cannot say that the Hamiltonian looks the same. But as far as there is no such h, only the coupling like this is present. There I can make this transformation that I say that tau is equal to sigma in one sublattice and tau is equal to minus sigma in the other sublattice. That introduces a negative sign here, and so the j less than 0 then maps onto the j bigger than 0, maps onto the ferro. So the thermal properties like internal energy, specific heat, etc. for this antiferromagnetic chain is going to be the same as that for the ferromagnetic chain with the same G. But the magnetic properties of course will be different. So let's just look at, talking about magnetic properties, let's just look at some correlation functions. So
when we were deriving the partition function for the ferromagnetic case, I couldn't see that which step there is like different from like what we are doing. Why is it z not this? So if I proceed in the same way as we did for the ferromagnetic case without doing this spin inverse transformation, which step fails?
no, that doesn't fail. We'll get the same thing except that they will come with a negative sign. But doesn't matter because hyperbolic cosine is invariant at that. So if you do the calculation, you should get the same result. Another way of saying that ferro and antiferro become equivalent is doing this transformation. It's not an alternative or anything. It's the same thing, saying it a different thing.
So then partition function.
And that is true. I mean, what I'm just telling you about, this is true not in just one dimension. Whenever you have bipartite lattice, it's true. So this 1 plus tangent that I could do only in one dimension. Higher dimensions becomes much more complicated. So I don't have to do that calculation myself, but I just say that I do this transformation that in one sublattice I say that the new spins are opposite to the old spins, and other sublattice you say that they're the same as the old spins. Then that just simply changes the sign of change.
But say if I don't do that transformation and derive the z, just like we did it for the Ising model,
Yeah.
we will get the same
You will get the
result.
same result.
And then if I say calculate the magnetization and all,
There you will see something which is very different.
yeah, so that's what I'm asking. Like,
So that's what I said now, whenever you have a magnetic field, then you cannot do the transformation. because magnetic field couples to sublattice A and B in equal. So if you change the signs of the splits in one sublattice, then you have not a magnetic field but what is known as the staggered field. That H couples to sublattice A in one way and sublattice D in the opposite. So whenever you are involved in magnetic properties, those will be very different.
Is it possible in 2 dimensions?
This transformation you can do on a 2-dimensional square lattice. I'll show that. Yeah. It has to be bipartite. That it has to be divided into 2 parts, such that if you look at site in lattice A, sublattice A, all its neighbors are in sublattice B. And similarly, if you look at a lattice in site in sublattice B, all its neighbors have to be in sublattice A. Which is here it is supposed to be a 2 dimensions. There are some lattices for which you can do that, some other lattices you cannot do that. So that is something that will be coming. So I mean, talking about this, I mean, just what we have shown here is that either do a transformation or just look at the result and change the sign of J to see whether the result changes or not. You get the same partition function when the magnetic field is equal to 0. But the correlations will be very different. And that also can be seen very easily. So do you remember the result that we got for the correlations in the 1D ferromagnetic isotope? What was that? So let's look at this. Sigma I plus L. This average is something that we had calculated for the ferromagnet. And that was, if I remember correctly, hyperbolic tangent beta J raised to the power now you see the difference. Cosine hyperbolic is invariant at J equals to conjunction. Tangent is not invariant. So tangent minus beta J is minus of tangent beta J. So when you take it to the power L, this minus sign will not matter if L is even. So if I am looking at this side, this side, this side, this side, those correlations will remain the same as what you had for the ferromagnet. But if I look at L is odd, so if you look at the correlation between this and that, or this and that, or this and that, take a spin from one sublattice and look at its correlation with the spin in the other sublattice. If you do that, then we'll pick up a minus. And that is to be expected because the arrangement of the spins that you have is like this. So if I look at the same sublattice and look at the correlation between this and this, then it will be similar to what you have in a ferromagnet. But if I look at the correlation between this and that, then this wants to be up, that wants to be down. So you get a negative value. The negative value is exactly negative what we get for a ferromagnet. So, I mean, that already shows that if you look at correlations, and today in the morning I told you about the susceptibility, that by summing the correlations you get susceptibility. So those things will be very different for this antiferromagnet as compared to the ferromagnet. But common properties like internal energy, specific heat, all those things, zero magnetic field, will be exactly the same as what we have for a ferromagnet. But of course the magnetic arrangement is different, so the magnetic properties like order parameters and things like that will be very different. Okay, is that clear to everybody? I am doing this 1D model in some detail because here everything can be calculated explicitly, and you can see the basic physics points that some things depend on the sign of J, some other things don't depend on the sign of J. So, but you have to be careful about what you are looking at and how it depends on whether the sign of J is positive or negative. So here J is just let me write it down because that's interesting to look at. Times data J magnitude raised to the power L and minus 1 raised to the power L. Because the J is now negative, so I write this J as minus J magnitude, and tan is the odd function, so there's a minus 1 coming from there. But then there's a L there is power, so it's minus 1 to the power n. So L is even, then we'll get the same sign. L is odd, we get different sign. Okay, so now we go to 2 dimensions. So 1D is instructive, but well, actually there are many 1D materials also these days. People actually can do experiments on materials where the structure is such that there is one line of something and that it doesn't interact very strongly with similar things in some other line in the lattice, and approximating the system actually can be thought of as 1D, but it's a kind of not what you see in everyday life. And there are things like carbon nanotubes and whatnot. There again, effectively one can treat the system as one-dimensional and one can do the 1D physics. So now with the same model, we look at it in 2 dimensions. And keep matters simple, I will look at 2-dimensional square lattice. These are the lattice sites. Now just go back to what we are talking about 1 dimension. Because the question is whether this lattice is a bipartite lattice or not. It can be divided into 2 sublattices such that if I look at, as I just said, a particular spin in one sublattice, its neighbors must belong to the other sublattice. And here we can do that. I mean, that's something that's fairly easy to do. So I'll just write this A, B, A, B. So if I look at A, all its nearest neighbors are B. Similarly, if I look at B, all its nearest neighbors are A. So this A basically defines a sublattice, which is again a square lattice. Because if I just connect all the A's, they can end up with the square lattice, take it relative to the axis that we have drawn. If I look at D's, again we'll get a square lattice. So this square lattice is divided into 2 sublattices. And it is also bipartite. That if I look at a B, then all its neighbors belong to A, and similarly if I look at A, all its neighbors belong to B. And so what we are talking about in the case of 1-dimensional model, very similar things can be done here also. The difference is that in 1D, as I've been trying to emphasize, there is no ordered space, but in 2D there will be an ordered space. And from what I've told you, we should be able to guess that the phase transition in this 2D case, going from the disordered to the ordered state, its behavior should be very similar to the behavior that you see for the ferromagnetic model. How do I do that? I mean, I just do this transformation. That in the B sublattice, I define a new set of spins which are negative of the A sublattice. And then the fact that J is negative goes away, J becomes positive. Because every time I do sigma J, I am taking one spin from sublattice A and one spin for sublattice B. These nearest square interactions always are like that. There is one A and one B. So if I define new variables which changes the sign of spins in one sublattice, then that introduces an extra negative sign, which then makes J positive. So thermal properties of this are going to be the same as thermal properties of the ferromagnet. I think ferromagnet in 2 dimensions, the same line, the same talking part. But of course, magnetic properties, correlations will be very different. So ordered state of the system is where you have A sublattice, you have spins up, B sublattice, you have spins down. There is an equivalent ordered state where everything, B sublattice the spins are up, down, and the B sublattice the spins are up. These are related to each other again by this spin reversal summation. So now, I was talking about order parameter. So how do you, does this answer your question? You had some questions about whether it can be done in 2 dimensions or not.
It's clear, sir.
Sorry?
It's not clear.
It's got clear. So how would you now define an order parameter? So for the ferromagnet it was simple. Just take sigma and take the average value. It is 0 above certain temperature and non-zero below certain temperature. But here, one sublattice spins are pointing up, other sublattice spins are pointing down. So if I want to look at the total magnetization, that will be 0 in the order. So this order parameter will not go. What order parameter that we had for the ferromagnet, that will not go. So what one does is again define something which is called a staggered magnetization, which is basically magnetization in sublattice A minus magnetization in sublattice B. So, and then you can see that if I sum over all the spins in sublattice A and then subtract from that all the average values of the spins in the sublattice B, then I get back something which is non-zero. Yeah? So, let's just write down something that defines this staggered magnetization. Sum over I belongs to A, sigma I average, minus sum over I belongs to B, sigma I average, and you divide it by the number of spins. This is what we call M sub S. S for staggered magnetization. And this is something that will be non-zero only in the ordered phase, and it will go to 0 if there are eigenvectors. And then, as I said, just looking at the thermal properties of the transition, like specific heat. And here, in 2 dimensions, there is a 2 thermal phase transition. Specific heat actually has some kind of a divergence at the transition, but that will be exactly the same as that for the ferromagnet, because by doing this sublattice transformation, you can map the antiferro to the ferro. But now the fun begins. So this is simple. If you bipartite lattice, then you can simply do this transformation of sigma 2 minus sigma in one sublattice, mapping to the ferromagnet. For the antiferromagnet, thermal properties also you can calculate like that, just as we have done for the case of 1 dimension, coordinate functions, etc. But now, instead of simple triangular lattice, simple square lattice, I now consider a lattice which is like this. Elementary placate the triangles instead of squares. So we have this sides sitting there. And this lattice exists in nature. It is not something that one is inventing from imagination. There are materials which go into this kind of triangular lattices. And then we have this model on this triangular lattice. So then there is a problem. Can you see the problem? This lattice is not bipartite. You cannot simply break it up into 2 sublattices such that this condition is satisfied. And you can already see that if you just look at a single placate of this lattice, there is one spin here, and one spin there. And the antiferromagnetic interaction tells you that nearest neighbors are to be anti-parallel to each other. Right? So I start with this pin up. Then this pin wants to be anti-parallel to that, so this pin should be down. If I now look at this pair, again these two have to be want to be anti-parallel, so we have up again. But then you see that these two are not in a good position. That they do not give you low energy. Right? I am saying that this bond has to be lower energy, so I want this to anti-parallel. I want this bond to have lower energy. That also I make anti-parallel. In the process, I end up with a bond where the two end spins have to be parallel to each other, and that gives you high energy because the interactions are anti-ferromagnetic. So it says that antiferromagnet is not trivial when it is on a lattice such that all the bonds cannot be minimized simultaneously. This is a simple thing. I mean, it's just a question of little bit of thinking. So this is one configuration. But I could have made another configuration which is like this. What is different is that earlier this bond was higher energy, but now this bond has the higher energy. Similarly, I can also, no, this bond still has low energy, this bond has the high energy. This is parallel to each other. So by choosing which bond I put the high energy bond, I can have different configurations which will have the same energy. But we cannot minimize the energy of all the bonds simultaneously. That's just a property of the Hamiltonian, and that is on which you put the Hamiltonian. Nothing very fancy. It's just that saying that you start with one spin up, then you want to minimize three of it that happen. Three of it will never happen. So this is the one that I had drawn earlier. So here this bond is satisfied up down, this is up down, and this is not satisfied. If I want to make this bond not satisfied, then I'll put it up here. And this bond is not satisfied. This bond is not satisfied. This one is okay, it is up down. This one also is okay, up down. But now this bond is not giving you low energy. Earlier this bond was not giving you low energy. So you can also construct a configuration where this bond will give you high energy and the other two bonds give you low energy. So there are two things that comes from this kind of considerations, that there will be certain bonds where the bond energy cannot be minimized by choosing appropriate spin configuration. And the fact that they cannot be minimized, there is a name associated with this, and I think this is the appropriate name. It's called frustration because the spins are frustrated, so to speak, that they cannot arrange themselves in such a way that every bond requirement is satisfied. There will be always some pairs of spins such that for that pair you cannot get to the low energy configuration that is given by the Hamiltonian system. So the behavior of such systems is actually very interesting and also very complicated. And one of the things that I just tried to show is that even for a triangle, you can see if I look at the low energy states, then there will be threefold determinants. Because I can choose the frustrated bond, either this one, that one, or that. So it is not surprising that if you now look at a whole lattice with this kind of interactions, then there will be, if I look at the lowest energy states, will not find a single or two or small number of states which will minimize the energy. We'll find actually an extensively large number of ground states. So this kind of systems have this strange property that the ground state is ground state is highly degenerate, and the degeneracy actually is something raised to the power e raised to the power something times n, exponentially n. So this particular model actually there is people more or less understand what is going on, but there are many such other models that people have constructed with frustration, where you have a very large number of ground states, and the properties of those kind of models, finite temperatures, is something that one has to work on. In many cases, it's not understood how these systems will behave as a function of temperature.
So this is another example of violation of the third law.
Yeah.
It's a big finite entropy at zero.
Another example of this is something that I just mentioned that because Professor Verma talked about it, is this RKKY interaction. RKKY interaction that he wrote down, the sign of the J depends on the distance, and it can be positive or negative, oscillates. So there you can have this kind of a situation where there is one J1, one J2, one J3. These are three spins, and you have this interaction of J1, J2, and J3, and I choose this to be less than 0, this bigger than 0, this bigger than 0. And then again you can see that then you cannot satisfy all the interactions, pair interactions, because if you start with this up, then this wants to be up, we have a positive J, this wants to be up, but then you have two up spins connected by a bond which is negative, so that bond will not be satisfied. So if you have interactions which can be both positive and negative, and the sites are distributed at random, then you will have situations where there will be frustration, and this is what happens in spin classes, where you have this very complicated properties at low temperatures arising from the fact that there are very, very large number of low value states, not maybe quite ground states, but states with low energy, very large number of states with low energy, and that leads to various interesting properties of spin classes at low temperatures. So this is, well, one way of looking at antiferromagnets, and whenever you have negative J, there are all these possibilities of having frustration and large multiplicity of ground states and one more thing I want to talk about as far as this antiferromagnets are concerned. There are, again, many different kinds of magnetic order possible, and you may have heard about things like spin density waves. How many people have heard about spin density waves? Okay. Anybody else? Spin density waves, charge density waves, there are many materials which show this kind of periodic variation of spin density or charge density and things like that.
Spin waves and spin density waves are same or different?
No, very different. Spin waves are excitations from the ground state of ferromagnet or antiferromagnet. But spin density waves tells you about the magnetic order in the system. So one thing that is very easy to show from here is that this antiferromagnet can be thought of as what we call a commensurate spin density. Okay, so I just wanted to introduce you to spin density waves because that's there in many cases. So what is this? How do I write this? How do I describe this antiferromagnetic state? So my claim is that for this state, where A sub that is the spins are up, B sub that is the spins are down, I can express that by saying that sigma I average what is A is this lattice spacing. Lattice spacing is equal A. And does everybody believe that this is possible? Or what is the sigma E average is some number. This is magnetization, but in the magnetization is positive in A sublattice and negative in B sublattice. And the fact that it's changing sign as one is going from one sublattice to another can be expressed by this result. But this Q is pi by A, pi by A. The two-dimensional vector, x component is pi by A, y component is also pi by A. My claim is that this, I put this Q here and the R's corresponding to sublattice A or sublattice B, then it will give you positive magnetization in one sublattice and negative magnetization in another sublattice. That everybody agrees with that? Yeah? Yes or no? Everybody? So basically you see that what is happening here is that the average value of the sigma is varying in space with some wave number. That wave number is simply this wave number, pi by A, pi by A. And this is commensurate because this gives you the same value of n. For example, when this is in the one sublattice and minus 1 when it is in the other sublattice. And why does it happen? Because if I look at, let's say, A sublattice, I take this to be the origin. Take another side in the A sublattice, then the x coordinate and y coordinate, if I look at the sum of that, that will be always even. So here, this point is what? This point is A. Right? We have got one A in this direction, one A in that direction. Put that back in here, then we'll get a pi from here, a pi from here. We'll get 2 pi. So if you're looking at spins in the same sublattice, then this cosine always gives you 1. If I look at B sublattice, then it's just, this point is what? This point is, x-axis is 0, y-axis is A. 0, A. Put that back in here, we'll just get 1 pi, not 2 pi. So that will give you the negative magnetization. So the values of this Q are such that you get plus 1, minus 1, basically, depending on whether you are in one sublattice or another sublattice. But this Q need not be. Here, for the antiferromagnet, I said that the Q vector associated with this periodic variation of the spin is pi by A, pi by A. It's a commensurate. It just gives you basically 2 pi's, certain lattice points, and so on and so forth. But this Q, if I define it to be some incommensurate thing with the lattice, so that it is never equal to 2 pi or multiple of 2 pi, then the spin will continue to vary. But this variation will not register with the lattice. In the sense that here the variation of the spins going from positive to negative and etc. is very strictly tied to the lattice. That one lattice it is plus 1, other lattice is minus 1. But if I take a different value of Q, which is incommensurate with the lattice spacing, what do I mean by incommensurate? You just look at multiplied by some x here and some y here, where the x and y's are not ratios of simple integers. These are some numbers like pi or something, not pi here, we cancel out, some number which is a real number, which is not a simple fraction of integers. So then this magnetization will continue to be a periodic function, but the period is not commensurate with the lattice structure. So then that is called, this kind of thing is called CDW, spin density, SDW, spin density wave. can also call the antiferromagnetic spin density wave because your average spin is varying as you are going from one side to another. But that is commensurate because this variation is tied to whether you are in the sublattice A or in the sublattice B. But if I choose the corresponding Q vector to be incommensurate with the lattice, then there will be some variation. Q will tell us about the wavelength of that variation, but that will not be sitting commensurately with the underlying lattice. So that's some kind of order that also is possible in certain systems, particular things like the Hubbard model, for example, that was discussed earlier. There are some theories of the Hubbard model which says that there could be spin density waves of this kind.
So can we take Q values between two sub-lattices A and B? Or just to confine with only B one time and next time only A? Or we can take the distance between A and B, Q values?
Q values, you can take to be anything. Right? What I'm saying is that if the Q values are taken to be like this, with this x and y equal to 1, then this quantity will have +1 value in one sublattice and -1 value in the other sublattice. So it is basically tied to the lattice. The variation of this cosine is a periodic variation. It is such that it changes sign as one goes from A to B, and B to A again it comes back to the same sign. But if you take some other value of Q, then that will not happen. It's very easy to see in one dimension. So here, I don't need to have this 2 pi value, there's only one component vector. So we will have basically up, down. If I want to draw a wave, then this wave will look like, there is a maximum here, minimum here, minimum here, like that. But the maxima or minimum of the wave are falling on the lattice sides. But if I take some arbitrary value of Q, then that will not happen. The maximum minimum of this wave will not register with that lattice. And that is called incommensurate. Then I say that it's incommensurate. When it is commensurate, it basically means that the variation of this cosine, its peaks and troughs, they basically are falling on the lattice. Okay, so I also wanted to mention a few other different kinds of magnetic order. Ferro and antiferro that we have discussed. Free magnets also, I think Professor Verma had talked about that. It's antiferromagnet, you can say, but spins on sublattice A are different from the spins on sublattice B. A sublattice maybe the spin's length S is large and B the length is smaller. So there is again alternate arrangement, but there will be net magnetization.
Just a little question. I was wondering, as you showed in 1D XY model, there are these kind of excitations which kind of rotate slowly along the lattice. Now, if say I have a antiferromagnetic XY model, what kind of excitations destroy the order? Like what kind of?
The same thing. So you see that there is still sigma equal to minus sigma symmetry is there. So there is one state which is A sublet is up and B sublet is down. There is an equivalent state where it is A is down and B is up. So domain wall will be between these two states.
But are there these zero energy excitations also possible? I am asking about zero energy excitations.
If you have antiferromagnetic XY model on a bipartite lattice, then it's very similar to the phenomenon.
Full rotation of the spins.
So although I have the picture here where A is up and B is down, there is completely equivalent state where A is down and B is up. And you can create a domain 1 between them. And how will the domain 1 look like? That again is something which is instructive. Here you are always looking B, A and B next to each other. You have two A's next to each other, two B's next to each other. That is basically a domain 1. So ferromagnet has been talked about a little bit. I was looking at Puig's book and he talks about something which is called the helimagnet, which is basically a spiral arrangement of magnetic moment. So I just give you an example of that. Okay, how many people have heard of this? Helimagnet, helical structure of the magnetic field. Order. This kind of new to me also. By the way, so what other kinds of magnetic order you're familiar with? Let's see, we can talk about that. Talked about that ferro, ferri, antiferro, then spin glass.
I heard this new thing called alter magnet.
What?
Alter magnet.
So, like how you have a SO superconductivity, a conductivity is equivalent D wave superconductivity.
Okay.
That's the magnetism equivalent apparently. Alter magnetism is like the D wave equivalent apparently. It's still very new, I think.
News to me. I don't know. Yeah, well, there are people here who work on experiments. So, is there any other kind of magnet that you have come across in your experiments? No? So, we have done what? First day we did paramagnet, diamagnet, and then we have ferromagnet, antiferromagnet, ferrimagnet, and then we also did a little bit of frustration and spin glasses. So, what else is there? I mean, certainly helimagnet is there, which is according to the book. And there are examples, I mean, it gives not just picture, but also some materials.
Is heavy magnet spin
And
spiral?
spin density wave is another thing that, in commensurate spin density wave, etc. That is there.
So spin spirals are heavy magnets, isn't it?
Somewhat like that, yeah. So, let me just mention what he talks about. So, it's a layered material. Layered material, so there are these planes which are parallel to each other. And on each plane, the spins are coupled to ferromagnetic. Okay? So, roughly speaking, we say that there is a magnetization in each of these layers. And then the question is how this magnetization in the different layers, how they look relative to each other. Okay? The helimagnet is something that if I now look at this layer, and if I look at this layer itself, there will be, let's say, some magnetization pointing in some direction, called the X direction. So this is this layer. If I look at this layer, there will be a tilt of the magnetization from the x-axis by some amount theta. And this continues, that if I look at the third layer, again there will be a 2 theta t. So as I am going from one layer to another, this magnetization is rotating by this angle theta. Going from this one to that layer again, the amount of rotation is taken. And so it will continue. And depending on whether this theta is commensurate with 2 pi, 360 degree or not, it may or may not come back to the same orientation. Right? This is what one was talking about commensurate degree, whether it comes back to the same orientation after a certain number of steps. So this, if I now look at from the top, this will rotate. This will rotate as we go from one layer to another, continue to rotate by this angle theta, and go further. On this side you can also go. So this is sort of like physics, that there is some rotation as you've gone from one z value to another z value. And this sort of, the possibility of this kind of an order depends on what is the interaction between this layer and its next other layers. Within each layer, there is a big magnetization vector. Let's say it's already ordered. It's ferromagnetic interaction. And the kind of materials for which this works is that if you have now ferromagnetic interaction between these layers and antiferromagnetic interaction between next nearest neighbors. See, this is one more complication that I didn't go into, because in all the models that I looked at, they sort of assumed that there is only nearest neighbor interaction. But that is not always true. Exchange interaction has some range, it's short range, but it has some range. So depending on the material, sometimes you can have also next nearest neighbor interaction. And that can cause many complications. For example, I mean, in antiferromagnet, for example, people have looked at situations where the nearest neighbor interaction is one sign, next nearest neighbor interaction is a different sign. So it's ferromagnet for nearest neighbors or next nearest, I don't know, there's all possible combinations are possible. And trying to figure out what is the actual ground state for such combinations of nearest and next nearest neighbor, that itself is a problem that sometimes it is difficult to figure that out. But here there is one example where the interaction between the moments here and the moments there is ferromagnetic, but the interaction between the moments here and the next nearest neighbor, as I go to the next nearest neighbor, that is antiferromagnetic. And you can calculate something that I don't want to get into, little impression. So if you have magnetization here, each layer, the magnetization vector has the same magnitude. So the interaction will be basically, if you look at one layer, then it interacts with 2 neighboring layers. And if this ferromagnetic interaction is J1, and if it is J2, and so the energy of such a step will be basically minus 2J1 cosine theta minus 2J2 cosine 2 theta. Because this interaction is J2, and the difference between this and that is 2 theta. So it's a cosine 2 theta. I mean, just assuming that it's XY diagonal model or something like that. And the nearest neighbor interaction is going to be J1. There are 2 nearest neighbors, one on this side and one on that side. 2J1 cosine theta. And depending on, and one is saying is that J1 is bigger than 0, J2 is less than 0. One is ferro, other is anti. Then we have to minimize this as a function of theta that will give you what the actual angle through which the F is rotating as one goes from one layer to another. So this is also possible. I mean, I didn't know about it, but there are examples of that. So this is pretty much where I want to stop. I have one more lecture left, and there I will try to do some theory of the phase transition. So far, I'm just telling you that there will be a phase transition or there will not be a phase transition, what kind of ordered state is possible, etc. But systems, and the data that people got from magnetic systems were very useful in trying to sort of establish the various theories of phase transition that people have developed. So there is a close connection, but not so much emphasis is being put on phase transitions, at least what I am going to have been talking about. But that should be there in the sense that there are so many different phase transitions that one sees in magnetic systems. So one should have some understanding of how the phase transition actually works and what kind of interesting phenomena that one sees near one of those phase transitions. So that's everything up tomorrow. I spend on this.
Questions?
Can we find spin density wave in this type of magnetic?
In type, yes, I mean in some sense this is actually a wave. I mean, density is not changing, the direction is changing. But in principle one can also have a situation, but magnitude of m is changing as well as its direction. So I mean, things are going in some sense, in a periodic manner. It's not a periodic that comes back to itself, but as we're going from one to here to there, things are changing by a fixed amount. Here to there, this sort of looks like a wave. But the wave can be either in the direction of the spins or in the magnitude or in both. So in principle one can think of spin density wave states in this kind of layered materials also. There is actually, I think, Mustafa, did you work on this any models at any point?
Yeah.
So the postdoc, Michael Fisher was working.
Yeah, I didn't work on any models with him, but I think I've worked on any models somehow. But,
So there you have this complicated nearest neighbor, next neighbor interactions.
yeah,
And you have many kind of
it's
wave-like structure also.
It's very similar to what you said, except for Ising spins. So suppose you have even a linear chain, just a linear chain with, actually the linear chain in real life represents sheets of 2D stacked materials. It's very strong ferromagnetic interactions within each sheet. And coupling between two layers and their next layers. So you can forget about the sheet structure, just talk about a spin. So then it becomes 1D. So there's a 1D Ising model with nearest neighbor, let's say ferro or anti-ferro interactions. It doesn't matter, let's say ferro. But second neighbor anti-ferromagnetic interactions. So then the question is what would happen? Now, if the first neighbor interaction is strong, then you forget about second neighbor, it will become a ferromagnet. But if the second neighbor interaction is strong, then you'll have a structure which is up, and then second neighbor should be down, something down. I can't do it in my head, but okay, something like that. Yeah. Certainly not.
Some kind of modulation, spin modulation.
Spin modulation. Now, if you ask, if you change the ratio of the two couplings, and you have an axis ratio of the couplings, what will happen? On one side you have one, on the other side you have the other, and there's a first order transition suddenly from one to the other, as usual. This is understandable. What is remarkable is that the point at which the first order transition happens, there's an infinite number, strictly infinite number of degenerate ground states. Okay, and the character of the ground states is also interesting. I mean, some are up, then down, up, down. So they are like, okay, anyway, I won't get into that. And then that shows itself, okay, so that's long period structures. Now, interestingly, if you raise the temperature a little bit, the temperature removes the degeneracy. It's like some jump. So you have whole phases of each one coming up. And there's a whole sequence. So there's one point at which an infinite number of distinct thermodynamic phases meet. Yeah, it's called a multi-phase point. It's a very interesting thing. And the physical realization of this, not so much in magnets, but in a material called silicon carbide. Have you heard of silicon carbide? It's a very hard material. Now, silicon carbide at some temperature, which I forget, has a whole sequence of phases. It shows this and that. There's a very nice simple mapping to the model I just mentioned, which explains why this is happening. The name of the model is ANNI. A-N-N, one more N, and then A3 N's are ANNI.
Axial next nearest neighbor.
Exactly. Axial, what is it?
Next nearest neighbor.
Next nearest neighbor. It was introduced by Roger Elliott. But it became a source of controversy, the sequence of phases near zero temperature. So Fisher and Semke worked on it. They got it wrong.
I see. Something mathematician got wrong.
How? Because they did the low temperature expansion. Somebody made a mistake. But then Fehrenbach did simple mean field theory and he got it right.
And this removal of degeneracy by temperature also is something very interesting.
Very order by disorder.
Order by disorder.
Yeah, it's called order by disorder. Temperature is supposed to induce disorder, but it induces order. That's my naive understanding. I think there's more to it, right? Order by disorder.
Something like that. If it's large degeneracy, then that doesn't give you any knowledge.
Yeah.
Order.
Exactly.
Remove some of the degeneracy, then that might be good.
Magnetism is quite fascinating. Also, I wanted to add, sorry, somebody was saying something? Yeah. Who is, somebody was trying to say something. Put up your hand. Because
he was saying that you should use the mic.
Oh, okay. I'm using the mic. Okay. All I wanted to say is that these sort of spiral orders, so you talked about the sort of flat spiral,
Yeah.
but then also conical spiral.
Yeah.
And so
You
on
can
and so
tilt
forth.
as
And some of them occur, but I can't remember, in the elemental rare earths. So look at elemental.
chromium or something, I think.
That's what I also recall. That Wikipedia couldn't find it quickly.
Yeah.
But anyway, Wikipedia doesn't know everything. Yeah, it's fascinating actually.
Okay, so any questions? I would be actually curious to know if there are other kinds of magnetism.
Yeah, there must be. What was this element?
So, quantum magnetism says that you have a regular antiferromagnet. You have an antiferromagnet, but the difference here is that the electronic bands are not Kramer's degenerate. So the band structure depends on the wave vector in a spin dependent. Apparently, the illustration is that you have an antiferromagnet, but the bands they've drawn some kind of shape for the band, and it's changing. Depends on the orientation
There
of
are
the spin.
separate up and down bands.
Well, I'm not very sure what Kramer's degenerate means.
That is a very basic thing. I should have said it in my atomic thing also. Or maybe you could say it. Kramer's degeneracy.
Okay, so there is overall zero magnetization, but the Kramer's degeneracy is still broken, which is, I think, very nice. But that's what this field is.
Actually, you can do that if you consider a polymagnetism type. If we consider the poly type picture where you have a ferromagnetic picture where the bands are slightly shifted, the Fermi level for the up and down are different. So that if we think of it like a harmonic, the parabolic type.
Yeah, parabolic.
So to make it a ferromagnet, you just shift it along the energy axis. Instead of doing that energy axis, you can tilt it like third kind of wire semi-metal, how they tilt the cones. Similarly, you can tilt the cone, so then the degeneracy is broken, but net magnetization is still equal and opposite basically. So that's the band diagram that I'm sure somewhere it will be there.
Okay, I'll look it up because something
But
that's
since Kramer's degeneracy is mentioned, let me just say what it is. I don't know what say on this, but I'll tell you the implication. If you have an odd number of electrons, then it's impossible to remove all degeneracy. See, we did many complicated things. We did L and S and then combining and crystal fields and no matter what, if you have an odd number of electrons, the degeneracy will stay. That is Kramer's theorem or Kramer's result. That is called the Kramer's degeneracy. With an even number of electrons, it does not mean that you can't have degeneracy. You can, but you can also have states with no degeneracy, namely singlet states. I mean, J equal to 0 states. But with odd number you can't. So that is the implication of the Kramer's theorem.
So how is Kramer's degeneracy portrayed in magnetism?
We don't know, we've never heard of it. So, okay, so this is a good example. You all tell us. I mean, I don't know.